Okay, so I really have zero preparation, and also I'm kind of tired. I usually wake up at 7, but now it's 2:39, which is a good thing, but depending, I'm not really the best at, So, first let's to kind of talk about construction functions, right? So I'm gonna start reading first. I'm gonna try and, like, again, my goal is to solve at least, like, maybe 3 problems, just to make it simpler. And then, like, at the end, I'm gonna solve another 3 problems. I'd be like, so I'll solve 3 problems to, like, give myself a understanding of what the problem is. Or, like, understanding on, like, how to solve the chapters, right? I'm doing 4.2, 4.2, 4.3, 4.4. It's based off here. The here lecture here lecture syllabus. Now I should probably this is just for 2, 3, and then 4. Um, Apart from that, yeah, again, I kind of explained already. I'm gonna do like 4 chapters. Sorry, 3 chapters today. I won't have a deep understanding, but just like a more so that I'm not like. And this is just for the week too. So if I can get this down, I should probably be okay so far. So let's just begin because I don't know why I'm like complaining so much. So construction of functions. Main idea. Explain what a function is. Sorry. Explain what a function is, bro. A relation where every input is in the domain exactly one of the output. Yeah. This is essential. So given functions we already have, how can we construct new functions? So the main constructions are composition, inverse relation, restrictions, union piecewise. Let me see if it updates. Okay, it doesn't update at all. I'm just can do this. Can do it. These are just my so composition of functions. Let's see. Composition of function is the domain of a composition. Okay, so composition first, and then a domain. So x. So g equals x. Composition. Domain of a composition. So domain of composition. Okay, so composition, and then we're talking about domain of composition. And then why composition is still a function. 3, 4 inverse relations. Associativity of composition. Okay, so let me see. So we're talking about compositions. Why compositions? Inverse relations. Okay, inverse, yeah. Then associativity of composition. So okay, weird. Identity functions. Okay. Restrictions and extensions. Instructions and unions of functions. Piecewise defined. Increasing and decreasing functions. So we're gonna give it the properties, I guess. Alright, so let me see. Where are we coming from? In which every input is in domain appears. Wait, just to make an understanding, isn't like a so I just want to tie back what a relation is.
I'm not. He can't go by himself.
Why? Brother, if you want your son high level wrestling, send him 2-3 years Dagestan and forget.
3 years?
Yes.
Yeah, you're out of your fucking mind. 2 weeks.
6 months,
2 weeks
one
he
time
goes-
you can call him.
2 weeks.
Son, high level wrestling, send him 2-3 years Dagestan and forget.
3 years.
Does anyone describe the relation as a set of ordered pairs and formally define the relation from A to B as a subset of A to B? Start with the Cartesian product. Suppose wait, so you're saying it's math for proof because we can replace it with the precise membership statement. We normally are not using relation merely to perform a proof. Instead, the relation is a mathematical object, and the proof determines what property that object has. So it's the relation is a mathematical object, huh? And the proof determines. Oh, okay, I get it. So let's say we want to prove whether this this thing right here is transitive or reflexive. Maybe you want to prove and to show that this is like like basically like let's show like say like this statement or this statement right here is like reflexive or transitive because we want to kind of like prove something of something of this sort, right? That's kind of what they're saying. So to like the I took caffeine, but I'm yawning all of a sudden. Weird.
Hey, Mark. Hi, I'm Brittany. Before
Okay, so I find it to be summarized by something. So you're right. So construction of functions. Where are we coming from? So section 1.1 asks, what is a function? A function is a relation in which every input is domain, so every input in the domain appears, every input receives exactly one output. So section 2, starting with functions we already have, how can we build new functions? Because functions are a set of ordered pairs, some operations may include only a relation, not necessarily another function. Therefore, the recurrent question throughout this section is, after constructing the new relation, does every input still receive exactly one output? That is the third connecting composition versus restrictions and piecewise functions. So what problem does composition? Uh, what problem does composition solve? Suppose one function performs the first step of a process, and another function performs the second step. For example, F takes a student and find their exam score. G takes a student exam score and assign a letter grade. To find a student's letter grade, we perform student's score grade. This combined process is composition. Gimme meaning basically is like this. This means put fx into x and put f of x into g. Function closest. So the function closest to x acts first. Even though g is written in first, f happens first. So here, remember, they say f happens first, so f is a, so gf of 1. Okay. So why must the sets line up? Suppose f maps A and B and G maps to B and C. The output f belongs to B and B is exactly the set of accepted by G. It's like checking in programming where therefore is valid. But if fx produces something outside the domain of G, the composition is undefined for that input. That makes sense. So the domain of composition. Obviously, I think it's a. So domain of g of f, or I don't know, f of g, if g of f, whatever it is equal to, for x in the domain of f of x is the domain of g. Oops, let me see. No. La. Doesn't matter. Dude, just chill. So domain of a function. So a g of f, right? Domain of d of f. So it's for every x in the set of domain of f, right? So essentially, domain of f is this one right here. Domain is like for every x in domain of f, the value of it seems that domain of g, which is b, I suppose. So I'm just gonna, okay, shit, I saw a domain already. I was gonna guess what domain is here. But, so looking at this, obviously the g of f is gonna be.
The number you have dialed is not available. Please leave your message after the beep. Hey, it's me. I know we haven't spoken in a while and things
Yeah,
have been
r
weird.
minus, basically, because you can't have the denominator
I just
0.
wanted to let you know that I miss you.
I need to keep in mind that
Doing really
when
good.
when this shows, this is a value basically.
Call me sometime, okay?
But the thing is, domain of G as well is
Bye.
they're saying f of x is an element of a domain of G. So acceptable inputs. So the output of f are the acceptable inputs of G. Sorry, basically. So basically, the domain is only here, right here. After f is in G, so here are all acceptable inputs, such as this works. So that's why it's r minus -2 and +2. Okay, so this one goes in deep. This one goes super deep into composition. Now, okay, so looking at like our first question here, find f of g and find g of f for each pair of real functions. Use the understood domains of f and g. This is okay. I mean, then all of these are practically fucking easy then, because g is just simply just and then g of f is the same thing too. And then the domain here. So the domain in this, so for I'll give it for instance for 2a, the domain here obviously. So you're gonna plug in. So obviously it's like 2x plus 5. Just put them in. So it's gonna be 6 minus 7. Then it's gonna be 2x plus 5, which, and then looking at that, the domain is all acceptable inputs, so it can be any real number. Okay, it's an and range too. So the range we haven't gone over there yet, but given what we know right now, we can probably solve 2a just for the domain. The range is still questionable. Okay, so remember they're kind of going deep into composition. Remember, like they kind of spoke to talk about composition like constantly. Composition is associative. Oh, wait, is associative? Okay, but here it's really. I didn't know what that was. Oh yeah, yeah. Okay, right. But from what I'm seeing right here, it's it kind of talks about composition, domain, the domain of a composition. What else they talk about? It's associative. Why it's a function. They give a lot of general rules around the composition, which yeah, it's not commutative obviously. Associative identity functions. I think the function. So that's it. The identity function on A is. Okay, so part two, inverse relations. What problem does inverse solve? So we talked about compositions, now we're talking about inverses. So what problem does inverse solve? The function tells us how to move forward. Okay. Inversing, can we revert the process and recover the original input? Because function is set up order pairs, forming the inverse means switching the coordinates. Thus, the inverse of f is the set yx such as xy is an f. Example, where the inverse is a function. Each of the inputs will receive exactly one output. So, inverse of f is a function. Example, where the inverse is not a function. I'm assuming is where yeah. Familiar example, let g of x is x squared. I'm all real numbers in. So wait, hold on. So remember, g of x is the value, x squared. So okay, it's x squared. So but why is it, I thought this was the y though, isn't it? Why is x, like it's literally x, so why is it, what? That's weird, I don't understand that one. Okay, so part two, kind of talking about inverse of inverse relations, inverse functions. Talking about domain, not a domain. What is a function? Sometimes it's a function, sometimes it's not a function. And gives examples on top of it too. So why inverse compositions give identity? Okay. So it gives it identity. Okay, I see. If we apply x and then reverse it, we return to exactly where we started. I see. Restrictions and extensions. What is restriction? Restriction uses the same function rule, but allows fewer inputs. Suppose, and D is a subset of A. So the restriction of F2D is written as, so restrictions and extensions. Human reasoning, keep the function but turn off parts of its domain. Example, with domain, the restriction is since is no longer R but only positive numbers. I see. Because their domains are different. Why restrictions are useful? Earlier x squared did not have inverse. But restriction now, the inverse can be. Okay, I gotta see now. Okay. Okay, so here's how our restriction functions, and now intersections and unions, which I'm pretty sure is kind of intersection where obviously same rules, not that hard. right here. Union again, simple, pretty simple, not that hard. Piecewise functions. I don't think this one's. Oh, so x squared if x is less than or equal to 2. This one again, simple. Increasing, decreasing functions. What is I in this scenario? But yeah, no, this one's simple, and then standard increasing proof. So okay, so just to okay, so domain and range. So I just want to kind of give us a rundown a little bit. Cause I still have 30 minutes left. So first we kind of talk about composition, its properties, its associativity, I guess the definition for the most part, and so composition, definition, why it's still function, inverse of it. No, not really inverse. I think the most of the part it gave us the example of a composition isn't really so yeah, I think part 2 talked about the inverse of it, or I believe so, right? So again, part 1 again, associative, why it's an inverse, when it can be a function, it's not commutative. So again, I'm just with my eyes right now. So the composition kind of tells the definition, what it is. I guess the question, what problems does composition solve? So yeah, just let's kind of go back to composition for the most part. Composition is simply I guess when the input of a function, so when the input goes into a function and that function's input goes to another function, that's what a composition basically is. And I guess this chapter is simply parts of yeah, okay, so it's simply talking about the construction of the. Okay, so we're talking about how we can build new functions, huh? Okay. Well, yeah. So that's one big clue. I guess actually the first thing I should probably touch on is what a function is, I guess, or not even a function, but I guess first is probably sets, and then a Cartesian well, no, Cartesian really doesn't matter. the sets, and then why what a relation is and why a function is a relation. So, relation is a part of a set. Sorry, no, yeah, relations. I mean, relation simply put is just a subset of two of the subset of a Cartesian product of two sets. It's an ordered pair, and as such, function is a relation where every domain is mapped to a output. So every A has a B. So for the pair, instead of for the pair x y in a relation, every x has a unique y. So with that, so on that note, what does this have to do with constructing? So what does that do with proofs for the most part? We simply use relations to define sets. To define a set where we can give characteristics on I guess we can give like certain we can prove certain characteristics on a predicate, I suppose. So we can show that it's transitive, reflexive, it's equivalence relations, etc., etc. So on that notion, what are we trying to do here now? We're trying to give more of a roundabout, more properties, I suppose, of functions. One is a composition, I guess. So composition is simply combining two functions to get. I guess composition is composing two functions. The important property is the mapping. It's not commutative. It's associative, but that's based on three. It's associative. It's not commutative. I think what else is there? What else did I miss? Yeah, it's mapping domain. Okay, so domain obviously it's just all values of G, all values of the. Okay, so why is it a function? I guess yeah, that's a good question because like yeah, it's not commutative. It's associative. Identity functions are off inverse of the inverse of f. Sorry, like the inverse of f on f is obviously is x. Inverse relationships. What else? Yeah, I know restrictions and extensions. Intersections. I mean, that's pretty simple. So this one's just like kind of the properties of. Okay. Yeah, I'm just gonna give myself a little break. Goodbye. onto one. So, so functions that are onto one to one functions. Okay, functions that are onto. So in section 4.1, we learned that what makes a relation a function. And every infinite domain must be. In terms of order pair, every element of A must appear exactly once as the first coordinate. Section 4.3 now asks a different question. What is happening to the outputs, to the second coordinates? There are two important possibilities. Onto. Every output in the codomain is used at least once. One-to-one, every output is used at most once. This section is not an introduction to a new kind of object. It's introduced to properties by a function. So the big picture. So for a function that's mapped from A to B, think of A as. So think of A as the available inputs and B as the allowed outputs. A function already guarantees every input in A. Every input in A has exactly one output in B. 4.3 examines how the elements of B's are used. Onto, no output in B is missed. One-to-one, no output is repeated. And both, every output is used at least once. Neither an output is missed and another output is repeated. And you also remember this. The reason to remember this entire section is the entire section. The function first coordinate is used exactly once. Onto second coordinate is used exactly once. One-to-one. Second coordinate is used at most once. Okay. So onto functions. Definition: a function is map A to B with onto B for surjection when the range of f is equal to b. Okay, I see. So the range of f is basically the codomain. In quantified form, for every b in the set B, there exists an A such that fa is equal to b. In human reasoning, pick any desired output in the codomain. So pick any desired output B from the codomain. There must at least be one input A that produces it. And remembering that, looking at that, knowing that f is a function, that means every single basically it's one-to-one, I suppose, or onto, if that makes sense. Why the codomain matters? Consider the rule fn equals 2n. If f is mapped into all natural numbers to the set R, then f is not onto R because it only produces positive even natural numbers. It misses outputs such as 3, -1, and 1/2. Wait, why does it miss outputs such as 3 though? Oh wait, because it's 2n, that's why. Okay, so now the proof now. How to prove that a function is onto? Let you prove that f(a) is mapped to b is onto. The proof structure is let b be your arbitrary. Let b let b in set b be arbitrary. Work backwards from the equation fa equals b. To determine what a should be, verify your chosen a is actually belongs to a, substitute into f, and show that fa equals b. So you're working backwards from the equation. So you're working so you know what b is. And now you need to find out what fa is essentially, and I'm assuming you gotta do it for every single value of b. Or yes, that's for like ones that like are simple, but I'm assuming this is like essentially was sorry like in a proof wise, in the proof case, it might be a bit more abstract, so we might not. So for essentially it's the proof would be a lot more like let x equal b, for instance, and then show that b is a element of a input for all inputs. Basically here, this is kind of what I was assuming. No, not really, but so let b equal b obviously, and choose a. Since we know a, then essentially. Oh, so we have a pre-image. I'm super sorry. I just took a really stupid fucking long break. So example, proving onto. So for f mapping onto R to R, we want to prove that every real output can be produced. So for let b equal R, b, so let b and R. We want f x equal b, so they're gonna work backwards. So x plus 2 equals b. So we solve backwards, x equals b minus 2. Because b is an R, we also have b minus 2 equals R. So now substitute. So now you have x equal b minus 2. So we put that in here. We get b. Therefore x, okay, I see. So that's how we prove. We gotta prove f of x is equal to b, which, yeah, that makes complete sense. What happened? We did not begin with a random input. We began with the desired output and constructed an input with that produces. That is the central idea of an onto proof. How to prove that a function is not onto? So to prove, you don't need to check every output. You just need to find where such that no a can satisfy this. Example: let g map from the set R to R. Let g of x equal x plus 1. So remember, the first things we gotta do is work backwards. So we know g of x equal to b. So since x squared is greater than equal to 0, x plus 1 is greater than equal to 1. Therefore g of x can never equal to -2, but -2 is an R. It's the codomain. Okay, I see. So basically, we just gotta find one. So because -2 is never it's never in, but it's in the codomain. Therefore, it's this is not onto. So 1 to 1. Okay, so now let me just kind of give a preface. So we define I guess onto functions for the most part, the big picture. So onto functions, and now we're talking about 1 to 1 functions. I'm guessing the next one will be what else? That's actually it. So 1 to 1 functions. So function f mapping a to b is 1 to 1 or interjection when f of x equals x. So sorry, it's a 1 to 1 function or injection when fx equals fy implies sorry if fx equal fy then x equals y. In a quantified form, this must be true. In human being, two different inputs are never allowed to produce the same output. Equivalently, if x does not equal y, then um, fx does not equal fy. So that's a one-to-one function, I see. A one-to-one does not mean that every input has one output. In every function, every function already has exactly one output for each input. One-to-one means each output has at most one input. Okay, I see. How to prove a function is one-to-one. This is a standard direct proof. Let x, y, be in A. Assume fx is equal to fy. Use algebra or definition of f to prove x equals y. The standard template. So let's look for an example, right? Where x equals 2x plus 1. So use this. Use algebra, which obviously, and how to prove a function is not one-to-one. I'm pretty sure the same thing. So right here, x squared. So xy equals y squared, and oh, so okay, so find two different outputs where, okay, that makes sense. The domain can change the answer. So consider f of x or x squared as a function from R to R. It is not one to one because f2 is f2 equals f negative 2, but as a function, the mapping is from 0 to infinity. It is one to one. But suppose xy is greater or equal to 0, and normally this gives x equal y or x equals negative y, but because both are x and y are non-negative, the second possibility cannot give two distinct values, therefore x equals y. So one-to-one depends on the domain, just as onto depends on the codomain. Okay. I have to read this again. So horizontal interpretation. So four possible types of functions. Let us use small finite sets. So the difference is obvious. So onto but not one to one. Let a equals 1 to 3, but the b is another thing. So both a and b are reached, so it's onto. The output a is repeated, so it's not one to one. 1 to 1 but not output. No outputs repeated, so it is 1 to 1. Output T is missed, so it is not onto. Both 1 to 1 and both onto. Neither. Composition of functions. The composite of G of F maps A to C onto composition theorems. If A is onto B and G is onto C, then G of F is onto C. Human reasoning to reach. Okay, what's the next one? Restrictions and unions. Pseudocode okay. Interpretation. Common proof mistakes. So clean summary onto functions are f a equal to b. Every codomain element is reached. Range equals codomain. Proof. So proof, and then 1 to 1 is different inputs cannot have the same output. Proof. Assume. Okay. So it's I get here. So for onto, every codomain element is reached. So from what I'm gathering, so basically because it still functions, so every input has output basically, and every output is unique. Here it seems that different input cannot have different outputs. So here the code. So let's say like there's like, so there can be like 3 and then 2 elements, as long as. So onto, for the most part, what I'm getting from onto is alright. There can be like 3 elements in A and 2 elements in B. As long as those 3 elements are included in A, so as long as those 2 elements from B are mapped to A, it's onto. For 1 to 1, So I think so here this is mostly just talking about on one to one and onto. So remember we wanted to prove remember this is all about sets for the most part. So this is strictly just it seems to be just onto for the most part. Sorry, I just repeated myself.
Fox News is streaming live on Fox
What the
One.
hell?
Watch the world change as it happens live.
Breaking tonight, we are following.
This is remember, this is mostly as like this kind of state. It's mostly just onto and one-to-one functions. I will go back to this, but it doesn't seem like this is such an important topic. So I think I'll just jump straight to 4.4. So looking at the reconnecting everything to sets, obviously, human reasoning of inverse. Inverse function undoes what the original function did. Yes. So why one-to-one is necessary? Why onto is necessary? And then here, bijection, perfectly reversible functions. The clean connection between one-to-one and on. So restricting the main composition and identity function. Example defining inverse function formula. Oh, inverse formula. I mean that's just simple. Just reverse here. So 2x equals 3. Just swap y and x. Permutations. Interesting. How to approach a common proof questions. Common mistakes. Okay, so there's 15 points. I should give this case, sorry, this what's it called? Some respect, because obviously they're taking a whole class period to talk about it. So I will just look at this and then do some problems here. So okay, so here it's actually which of the following functions map onto the codomains? Prove each of your answers. I'll just take a 3-minute break and I'll be back. Okay, so remember, I didn't really. So this topic really touches on two and 1-to-1. Onto simply, from what I've seen, onto is mostly as long as each value in B is mapped onto A, And for one to one, it seems like as long as only so like for instance, like let's say there's three elements. So wait, sorry. As long as the range is a codomain, or essentially, like let's say there's three elements in A and two elements in B, as long as all the elements in B are mapped onto a single, as mapped at least one element, then it's onto. For one to one, as long as I think it's more as long as each it does, the range doesn't necessarily have to be the code necessarily to be a codomain, but each sorry, as long as for every B mapped onto it only has one input. That's what I'm kind of gathering from this, and I think that's kind of the gist of the. And it kind of talks about how to prove in such and so forth. So yeah, I think I can probably tackle one problem and see what we can do about it. Yeah, because I haven't really, I've been just reading for the most part. I haven't really been like struggling to do problems. Maybe because I'm just like, is this laziness, I suppose. But yeah, let's do at least one. Let's do so. Let's do 1A just for now. 1A. So which of the following functions map onto their indicated codomains? Prove each of the answers. Okay, got it. Okay, so we're asking, given a function r to r, which is basically like um, a is mapped to b, which r is mapped to r. F of x equal 1 over 2 x plus 6. So they're asking us now, which function map onto? So remember, onto simply so I wrote it here. So this is a. So remember, onto simply remember the range, or the size of the range is equal to the size of the codomain of of function f, by the way. So it could be 1, 6, 7, doesn't matter, right? As long as the range is mapped to the codomain, this is essentially onto. So now the question is, let's look at this, and so right here, so right the b we okay, so we know that the codomain of f is infinitely many. Now we just need to find one case where it's not. So obviously speaking, x can equal, let's say x equals 1 for the most, 1, right? This is I guess the question is, how do we prove whether this is onto or not? So remember 1 2 x plus 6. So let me see, I don't know how to prove it, so I will just go back to my summary, which I think it did explain how to do it, so let's go back there. So remember, fx equal b. Okay, so step one for the most part is f of x equal b, right? So f of x here, so f of x is, I believe, 1, 2, x plus 6 equals b. Now solving for x is simply b minus 6 over 2, and that equals x, right? Now, given this, this is now go, so this is b minus 6. Now this should be equal to b. So obviously canceling out, this gives you b minus 6 and then plus 6. So this equals b. So this is onto. And I think this essentially tells us that every single number so 1a is definitely on. So here, 1a here is on 2. And I guess let's give a more of a tougher problem. I would do this, but this is a class. Let me see. This seems like a class kind of problem. Let's do 1h. I don't think the problems are really hard. It's just a little bit. The setup might be a little bit intricate. Okay, so remember f. Okay, so here we have it. And remember onto simply to prove why there's onto, let's set this equal to b. So this would be b equals x minus y. Now since those are their values, plugging it into. Okay, so hold on. No, wait, let's not erase that. So we know fxy is equal to x minus y. So we want to prove whether. So I'm assuming here is now the hard part, because we have fx equal b. But what about the pair equations now? That's the question now. Is it a to b or something? We don't necessarily understand. We don't necessarily know. It never really gave us that definition. But we do know that it's paired to one real number. So this is a real number. Like the first one, it was fr to r, right? So I will probably take an educated guess and say, suppose in this equation, fxy is equal to b. So we know that the question is x minus y equal to b, right? So let's give fb, which is fx minus y. But that's only one pair, so it's not possible. Because it has to be a product, or not, sorry, a pair. It does pose a question. How do we solve such an equation like this? I think yeah, like many things requires inside knowledge. Now let's see I'm gonna look in the book and see if it gives you like a guess on how to do it. Okay, so there's one here where it said mapping is where M is the set of the set of Cartesian product uh of integers. I don't really have much time to do 4.4 because I gotta go. But remember, I just started at 239, so I'll just do some 2.2 problems. So that's back to I believe functions on two and yeah, it's a construction function really. Yeah, I'm just gonna do like several like maybe 5 to 10 problems maybe. Hopefully I can finish by sometime soon. I guess. Okay, so yeah, I'm just gonna give like a little refresher because I think okay, I'm pretty sure composition. So let's see. So constructional functions, where are we coming from? What is a function? Functions are relative. Yeah, so we did go back to like sets and relations and each function. So a function is a relation essentially that maps from a set A to set B. We know that for each, I guess for each A or for a function, the domain of a function must have all elements of A. And I think for here at the very least, we're not talking about onto and one-to-one functions yet. So we're just talking about simply just compositions and compositions, its definition. I guess also some other aspects around inverse, if compositions are associative, commutative, and such and so. Yeah, so not commutative, associative, then yeah, inverse relations. It's all practically yeah, restrictions, union, upper intersection unions. So here mostly just properties. Okay. So with that being said, I think problem solving is probably the question is, I wonder how many problems I need to do in order to have a better understanding on this question. But yeah, I guess for now, so what have I been doing so far? So I did produce number 2. I guess right now, let's see. Give to, okay, so looking at here, I am planning on doing 4A if possible. Let's see if we can solve this. So give 2 different examples of a pair of functions f and g such that f of g is 3 times 7 squared. Okay. So give a pair of functions f and g such that this is true. Got it. So this is asking us for some function where so I believe it's f and then gx equals 3x plus 7. Now no, this is basically saying something like this, right? So so from what I'm kind of, so there's not, jeez, this is actually a hard question. It's like if we were to do like nest it in, it would be 3 something like that, right? Tough question, really. So again, this is first thing we have to understand is the input. We're given this, and we want the output of, I guess, the output right now is functions. We want f of x and g of x. So remember, I have to still remember this is precisely what they're trying to ask us to do, and I guess no, I don't think factoring is gonna solve anything. Hard, hard problem, really. Yeah, I have no general direction of how to solve this, because I don't know how we can make, like, create a multiple that is directly out of directly out. So it has to be something like so something like, you know, x. So like let's put x and y here. It has to be something of a sort where like we're given like a value here, x, right, and then whatever this x is, which is like 3x plus 7, and then this has to be of y of something, and this y will be, so g, let's say g of x will be something like 3x plus 7, and then times x. So when you do f of g, and then you let x equals like 3. The thing is, this x is also implicating here too. So I guess like where I think of. So I have another direction too, since it's given squared. My thinking is like maybe g can equal, sorry. Can equal 2 no matter what. And then f But then, you know, so if I input, but it's gonna be also X here too, so it's not possible. It's actually a tricky problem. Huh. Hmm. Yeah, I can, so I'll just look for AI for this one. They got me. There, fucking hell, damn it. They got me. Fuck. So I guess I can do this. I can do B, correct? So B's this. So F of G. So that's and here one element, I guess, of TF5. Obviously, the variable is here. So looking at this, obviously f of x will need some type of square root. Now, and I'm gonna assume this is x of some sort, so g of x would probably just be so when you do this will give you I guess think of another example. So, I mean, honestly speaking, we can just like f, then g of x can just equal to, right? So if you do f g of x, this will give you. So those are two examples. Oh, I didn't really show you the screen, sorry, but it doesn't matter. Let's do another. So let me see. Oh, sorry, I'm looking at 15 right now. So let f equals map to A to B and g map to C to D. Define f. Okay, so define f to. Okay, so we know that the Cartesian product of f and g is AC, BD, AB, F, is an F and C and D is an G. Okay, so prove that. Got it. So let's look at 15. Oh, so here. This is then is in. I'll just put it right here. So prove that this is the input we're given, and so prove so the output what they want is let me see okay FG's and okay, so the function. So show this basically. Okay, so FG right here. Oh, they're saying so we know the set FG is sorry set set is simply this right here.
For the acute treatment of migraine with or without aura in adults, Nurtec ODT can provide relief in 2 hours. For the acute treatment of migraine with or without aura in adults, Nurtec ODT can provide
Yeah, first question, I forgot how to represent as an X, right? I generally forgot, but whatever it is, I'm pretty sure it's